Good day everybody. Today I'll be presenting you guys with a visual proof of one of the methods used to solve quadratic equations, known as completing the square. The aims of this video is to give the viewer an intuitive and comprehensive understanding of what completing the square actually is. Secondly, this video aims to give the viewer an understanding of why this method is called completing the square. I'll be making use of this quadratic in order to aid with the proof, in order to aid with the construction of the proof. And lastly, I'll be solving these quadratics using this method, and stick around for the last because I was solving the general quadratic using completing the square, and we'll derive a very well-known result. So stick around until the end. So first things first, the convention that we'll be using is that length is vertical, right, and breadth is horizontal, right? So we all know that the first step in completing the square is to get your constant term to the right? So it follows that the quadratic that I'm working with is x squared plus 4x minus 21 is equal to 0. Moving my constant term to the right, I'll have x squared plus 4x is equal to 21. Now guys, I want you to visualize this as the sum of some areas, right? Let me explain to you guys what I mean. Let x squared represent the area of a square with length and breadth equal to x, right? And you have it drawn visually. So visualize it, right? So here's a square with area x squared, right? So side length x and breadth x, okay? And then let 4x represent the area of a rectangle with length equal to 4 and breadth equal to x, right? So here we have it. Here's a rectangle, right? Its area is equal to 4x. Its one side length is equal to 4 and its breadth is equal to x, right? So area of a rectangle is length times breadth. Length times breadth, 4 times x, so 4x, right? And then 21 on the right hand side, it represents the area of a rectangle. So we don't know its length, it does or breadth, it also doesn't matter in this case because 21 is a constant on the right hand side. So the first step in completing the square is to cut this guy in half, the middle term in half, right? Take the middle term's coefficient, right, divide it into half and then square it. I will now show you guys why we do this. So first and foremost, let me just change this quickly. Okay, so you take the middle rectangle, right, the middle area, right, and then what you want to do is you want to divide it into two. You want to cut it into two, right? And then you'll be left with two areas, right? For this one, right, you'll be left with two areas. And this will be the two areas, right? You will have a side length of 2 and one length of x, right? And you will have another side length of 2 and a breadth of x, right? So this area over here should be equal to 2x, right? If I'm not mistaken. And then the other area here should also be equal to 2x, right? So 2x, right? That's the 4x. And I'm doing nothing, just right. I'm just dividing it into 2, and this could be similar as writing x squared plus 4x plus 2x, x squared plus 2x plus 2x. You know, that's what I'm doing. But now I'm gonna take this is where the visual proof comes in. I'm going to take this top area, right, and this bottom area and attach it to this x squared. Why can I do that? Because I know that the top area has a length of x and the bottom area has a length of x, right? I'll show you guys now what I mean. So I'll be drawing a square, right? Here's the x squared, right? There we go. That's our x squared term, right? Now attach these two terms, right? I'm gonna attach the bottom area first to the bottom of this guy. So it's going to look something like this, right? That's the bottom area that I'm attaching, and then I'm going to attach the top area of the 4x now. So it's going to look something like this, right? Exactly. And now I know that this area will be, this side length will be x, right? This length is, sorry, my bad guys. This side length will be x, right? And then I know that this length will be 2, right? Sorry, my bad. This length will be 2. This length will be x because I'm attaching it to that side. So that's where the x, that's this x, right? This side is this x, right? And this x right here is like basically this x here. You guys get me? So this is the x. And then this side is also 2, right? Because this is the area 2x, the 2x that I added. I took it from here, added it to the side. The bottom one, I took it and added to the bottom of the x square. Now, this is where completing the square comes in. I know that this area is somehow equal to an area of 21, right? That's correct. So I know that x squared plus 4x is somehow equal to an area of 21. Now I want to work with a perfect square, right? I want to complete the square, and this would be a perfect square, right? If I just had to add this area. What area am I talking about? I'm talking about this area here. If I had to add that, and it just so happens that my top side has a length of x and 2, so this length is x plus 2, right? This length is also x plus 2. This length is x, I know that, because this length is equal to this length, and this length is equal to this length, right? So I know that this is 2, and this is 2, and this is x, and that would make this a perfect square. If I had to add this area, this imaginary area of 2 squared, so 4, if I had to add this imaginary area of 4, right? This is 4, this is 4, sorry, my bad guys, this is 4, but this is the imaginary area that I'm adding, right, in order to complete this entire square. So that's where completing the square comes in. That's why this method is known as completing the square. But of course, whatever I do to the left hand side, I added an imaginary area of 4 here. I have to do to the right hand side, right? So that makes it not imaginary anymore. So goes plus an area of 4. This is just a visual proof, right? I hope you guys will see this as the sum of areas, okay? And then we have a perfect square on the left hand side in terms of x plus 2. So its length and breadth will be x plus 2. Why? Because I completed a perfect square. So I will have now that x plus 2, right, on my one side, and that's this length here, and this is the other side length here, x plus 2, and this is another 2, right? So yeah, we'll have x plus 2 on the side, and of course this thing would have an area of, you guys guessed it, its area would be x plus 2 squared, because it's a perfect square in terms of x plus 2. So area of a square, x plus 2, is length times breadth. So length times breadth is going to be x plus 2 multiplied by x plus 2, giving me x plus 2 squared. So that I know that area is equal to, since these are two constant areas, I just can add the sum and find a new area, right? So can go like that. It's equal to 25. So I know that I have to equate two areas, right? So x plus 2 squared, that area, the area of this square is equal to the area of this square or rectangle. You get what I'm saying? So x plus 2 squared is equal to 25. This implies that x plus 2 is equal to square root of 25. X plus 2 is equal to 5, or x plus 2 is equal to negative 5, right? So therefore x is equal to 3, or x is equal to negative 7. And we have just visually proved why completing the square works. So the reason why you halve this the coefficient of the second term and then square it is in order to find the reason why. Okay, let me repeat that. The reason why we halve this coefficient and then square it is in order so that we can add, in order to add this imaginary area imaginary area in order to complete the square, to make this a perfect square. But it ceases to become imaginary once we add it to the right hand side also, and that's why we halve the coefficient, square it, and add that to both terms, to both sides of the equation. So that is why, to find the area that would complete the square on the left hand side. Okay guys, I went to a new page, and now I'll just be using completing the square method to solve this quadratic. Okay, so we have x squared plus 5x minus 50 is equal to 0, right? First, step 1, bring your constant term to the right. X squared plus 5x is equal to 50, right? Step 2, look at your coefficient of your second term. In this case it's 5, divided by 2, right? And then square it. That would be the imaginary area that you would be adding. Yes, remember, right? This would be the side length, and this would be the side length that you'll be adding to x. Alright, so keep in mind what I'm saying. I'll come back to it later in the example. Okay, so 5 over 2 squared is equal to 2.5 squared is going to be 6.25, right? Then add that to both terms, so on both sides of the equation. X squared plus 5x plus 6.25 is equal to 56.25. I already added this 50 plus 6.25 is 56.25. Alright, and then we now have our perfect square, right? We can factor this into a perfect square of side length x plus 5 over 2, right? X plus 5 over 2 squared. And that is why I made a circle around this, because that is always the factor that you will find. Whatever you halve, right? After you halve the coefficient, you will always add that to x or subtract it from x in order to make it a perfect square, right? Okay, so x plus 5 over 2 squared is equal to 56.25. Therefore, x plus 5 over 2 is equal to the square root 56.25 plus minus. Let me just get my calculator to help me solve that. Square root of 56.25, 7.5. Okay, so it's equal to, so it's equal to 7.5 x plus 5 over 2, or x plus 5 over 2 is equal to negative 7.5, right? Because it has a positive and a negative root, right? So x is therefore equal to 5, or x is equal to minus 10, right? Or negative 10, my bad. There we go. And that would be completing the square. And okay guys, so here we have another example, but in this example the coefficient of the first term is not equal to 1. And notice that in order to complete the square, we always have to make sure that the coefficient of the first term is equal to 1. So we divide through by 2, right? Since the coefficient is 2, 2 divided by 2 is 1, right? So dividing by 2 gives us x squared plus x minus 6 is equal to 0, right? And now we can move on to the second step by moving the constant term to the right. So x squared plus x is equal to 6. Now we can look at the coefficient of the second term, which is 1, right? So it's 1. We divide it by 2, and then we square it, and that will be the area that we'll be adding to both sides, right? So 1 over 2, so it's going to give me a quarter, right? So I'll be having x squared plus x plus a quarter is equal to 6.25, or 6.25, right? So x plus 1/2. Remember guys, that's why I'm always going to draw a circle around that one. It's x plus 1/2. Whatever I squared, whatever I had to square, I'm going to write down over here again. You know what I mean? So x plus 1/2 squared is equal to 6.25. And then, you know, the simple steps follow after this. X plus 1/2 is equal to the inverse operation of squaring is square root, so plus minus 6.25, and x plus 1/2 is equal to square root of 6.25. Come on, man. Is it 2.2? 2.5, yeah. X is equal to 2.5, or x is equal to minus 2.5. Therefore x is equal to 2, or x is equal to plus, oh sorry guys, is equal to minus 3. And that's it. But last but not least, let us solve the general quadratic by using the method of completing the square. Ax squared plus bx plus c is equal to 0. And we'll be deriving a very, very well-known result. Just take a look at this, guys. Okay, sorry guys, someone just entered quickly, so I quickly got distracted. But where were we? Yeah, ax squared plus bx plus c is equal to 0, right? Then we to this ax, well, what am I doing? We divide through by a, right? So dividing by a gives us that x squared plus b over a x, right, plus c over a is equal to 0, right? And that makes sense, right? In order to complete the square, I have to make sure that the constant in front of the x squared term is 1, and in this case it is. Now I can move on with the further steps. Second step, move our constant term to the right. So we have that x squared plus b over a x is equal to negative c over a. Does that make sense? Okay. And then, in order to complete the square, right, we take our coefficient of our second term, right? Coefficient of our second term, b over a, we divide it by 2, right? And then we square it. But remember that when it comes to fraction, guys, dividing by 2 is the same as multiplying by 1 over 2, right? So, and I'm squaring that. So I'm getting b over a, so I'm getting b over 2a, right? And I'm squaring that in order to give me b squared over 4a squared, right? So that is my answer. That is the area that I'm going to be adding to both sides. Remember that, guys. Stick with me. X squared plus b over a x plus b squared over 4a squared, right, is equal to b squared over 4a squared minus c over a. Alright, guys. And sticking to the left hand side, x squared plus b over a x plus b squared over 4a squared is equal to, I'm going to join the fractions on the right, right? So I'm going to do it here on the side. I'm looking for common factors, so I'm going to multiply this by 4 and by a. So what I have to do on the top, I have to do on the bottom. So I have to add a 4a here, 4a. Does that make sense, guys? Is equal to b squared over 4a squared minus 4ac, right, over 4a squared. Does that make sense? Because if I have to divide 4a divided by 4a, I'm going to get c over a. Do you guys get me? Yeah, you guys get me. So I'm going to get c over 4a, my bad. C over 8. Yeah. Now that I can join these fractions, so I'm going to have b squared minus 4ac, right, is equal, all over 4a squared, right, is equal to, but remember, guys, this was the factor I used, right? This was the factor I squared. So I know that this is going to factor beautifully into a square with side length x plus b over 2a, right? So I know this is x plus b over 2a, right, squared is equal to b squared minus 4ac over 4a squared, right? So therefore x plus b over 2a is equal to plus minus the square root of b squared minus 4ac all over 4a squared. But I know that the square root of the fraction is the fraction of the square roots, right? So this is equal to b squared minus 4ac, right, plus minus b squared over 4ac all over the square root of 4a squared. But I know that the square root of 4a squared is just going to be equal to 2a. So this is going to give me plus minus square root of b squared minus 4ac all over 2a. And this is going to be x plus b over 2a, right? B over 2a. Now, in order to isolate the x and solve for it, I'm going to say that x is equal to negative b. I'm going to bring that over. It's going to become a negative b over 2a plus minus the square root of b squared minus 4ac, right, over 2a. But remember, guys, these are common fractions, or they have like common denominators, right? So we can add them or simply subtract them. You understand? So we can join these two fractions. So therefore, we will have that x is equal to negative b plus minus the square root of b squared minus 4ac all over 2a. And doesn't that look familiar, guys? This is the quadratic equation. So we have derived the quadratic equation by completing the square on the general quadratic. So try this at home, guys. Try to do this on your own. Yeah, just try to do it and show someone or something like that. Okay, good stuff.